Welcome to Botany A to Z. In today's topic, we will see the difference between NADH and FADH2. Moreover, we will see why the reducer form of NAD exists as NADH, but at the same time, the reducer form of FAD exists as FADH2. As you have seen in many biological redox reactions, that when we give 2 protons and 2 electrons to NAD positive, it does not become NADH2. Instead, it becomes NADH. At the same time, the 2 electrons and 2 protons provided to FAD convert it into FADH2. So we will see the difference, the structural difference between these two coenzymes. At the same time, we will see why NAD gets converted into NADH, but FAD gets converted into FADH2. As I already mentioned, both of these are coenzymes that act as electron donors, proton donors, or sometimes as electron acceptors and proton acceptors. It depends if it is in the form of if they are in their oxidized status. As you can see here, NAD positive and FAD, they will accept electrons and protons. As you can see in glycolysis or in the Krebs cycle or in the link reaction, they accept electrons and protons and act as electron proton acceptors. But when they are in their reducer form, the reducer form of NAD positive is NADH, and similarly the reducer form of FAD is FADH2. So when they are in the reducer form, they act as electron and proton donors, as you have seen in the electron transport chain, wherein they donate electrons so that the electron transport chain can run, and at the same time they donate protons into the intermembrane space so that a proton gradient can be created, which is used to produce ATPs. So both of these coenzymes take part in biological redox reactions. First of all, let us see their structure. Let us see the structural differences between the two. As you can see, the structure of NAD. NAD actually means nicotinamide adenine dinucleotide. So as is seen in this slide, the structure of nicotinamide adenine dinucleotide. This is nicotinamide monophosphate, and here it is adenine monophosphate. So the name of this compound is nicotinamide adenine dinucleotide, NAD. The oxidized form of this compound is as NAD positive. The oxidized state of this compound is as NAD positive, nicotinamide adenine dinucleotide 1 positive. Why it is positive? Because as you can see here, this nitrogen on the nicotinamide, it has 4 covalent bonds. As you know that nitrogen has only valency of 3, but here you can see there are 4 covalent bonds. As a result of that, this nitrogen has a positive charge. This is the oxidized state of NAD. So when we will have 2 electrons and 2 protons, as you have seen in the biological redox reactions during Krebs cycle, or in the photosynthesis, you can see it during photophosphorylation. The difference there is only that it is as NADP. So in these biological redox reactions, when 2 electrons and 2 protons are provided to NAD positive, here the NAD positive obviously will act as electron and proton acceptor. So when 2 electrons and 2 protons are provided to it, one of the electron will be used to finish this positive charge on NAD, to cancel out this positive charge. You have 2 electrons, 1 electron will be used to cancel out this positive charge on NAD positive. The other electron, the remaining electron, will convert one of protons into hydrogen. Electron plus proton is equal to hydrogen. So one electron has converted NAD positive into NAD. Another electron has been used to form one hydrogen atom. So NAD plus H is equal to NADH. This is the reducer form of NAD. The remaining proton will remain as such, because you don't have more electrons. You had 2 electrons, one of them you have used to convert NAD positive into NAD, another electron has been used to convert one of the protons into hydrogen, and the remaining proton will remain as such. So you will have NADH, not NADH2. As you can see here, that electron and proton which converted into hydrogen have been used here. So this is NAD positive. It has been given one hydrogen, it becomes NADH, and the positive charge on this N is finished now, is cancelled now. So you have, this is now NADH. The remaining proton will remain as such. So NAD positive plus 2 electrons plus 2 protons is equal to NADH plus H positive, not NADH2. Okay. At the same time, if we see this FAD, the flavin adenine dinucleotide, this is another coenzyme which is used in biological redox reactions. The oxidized form of this very coenzyme is FAD. It is not FAD positive. As you can see in its structure, the oxidized form is of the flavin adenine dinucleotide is FAD. There is no positive charge on it. There is no nitrogen which is having more than 3 bonds. Had it been so, there would have been a positive charge on it. So the oxidized state of flavin adenine dinucleotide is FAD. Now, when you will have 2 electrons and 2 protons, when you will provide FAD with 2 electrons and 2 protons, these 2 electrons will be used to convert these 2 protons into hydrogen atoms. In the aforementioned case, you had 2 electrons, you had 2 protons, but one of the electrons has to be used to cancel out the positive charge on NAD. Here in this case, we don't have that problem, as FAD is not existing as FAD positive, but in the oxidized state it exists as FAD. So these 2 electrons will be used to convert these 2 protons into hydrogen atoms. These will be added to FAD, and FAD will get converted into FADH2. This can be seen in this slide as well. So the 2 nitrogens which are marked with red, the 2 hydrogens that will be formed by the reaction of 2 electrons and 2 protons, those 2 hydrogens will be added to these 2 nitrogen atoms, as is evident from this slide. So you have 2 electrons and you have 2 protons. They become 2 hydrogen atoms which are added on these 2 nitrogen atoms, so that the oxidized FAD gets converted into reduced form FADH2. So FAD has the scope, it has the vacancy to accept 2 hydrogens. As a result, it gets converted into FADH2. On the other hand, as you have seen earlier, NAD positive can accept only 1 hydrogen. As a result, it gets converted into NADH. The remaining proton remains as such. So in today's video, we have discussed the structure of 2 coenzymes NAD and FAD. We have seen the structural differences between the two, and we have also discussed why NAD positive gets converted into NADH and not NADH2 when provided with 2 electrons and 2 protons, but FAD gets converted into FADH2 when provided with the same number of electrons and protons. So if you like the video, please subscribe the channel. Thank you.